Hi viewers, welcome back to our channel Raveendra for Students. In this video, we are going to see Gauss law applications part 2, which is the continuation of our previous video. Before going to start our video, if anybody watching our channel first time, please subscribe to our channel and watch all the videos, and if you like those videos, don't forget to click on like button. Viewers, in the previous video, out of the 5 major applications of Gauss law, we have seen the first 2, they are point charge and infinite line charge. And in today's video, we are going to see the remaining 3 major applications. They are infinite surface charge, infinite volume charge, and uniformly charged sphere. Viewers, in order to apply the Gauss law for infinite surface charge, let us consider our well-known Cartesian coordinate system consisting of the x-axis, y-axis and z-axis as shown. Now, again assume that the infinite sheet of charge is existing in the xy plane. So, in order to represent the infinite sheet of charge in the xy plane, we have to draw 2 parallel lines for the x-axis like this and 2 parallel lines for the y-axis like this. Then the bounded region of these 4 parallel lines will give us the infinite sheet of charge. Here let us assume that the x is ranging from minus infinity to infinity and y is also ranging from minus infinity to infinity. Then our next job is we have to consider a finite amount of charge. Then from that finite amount of charge we have to construct a closed surface called Gaussian surface. So for that, let us consider a small portion of infinite sheet, so that will become a finite sheet as shaded in the red color as shown in the figure. So in this entire infinite sheet of charge, the charge density is uniform. For every meter square it will have rho s coulombs per every meter square. Now to get the closed surface called Gaussian surface, so we have to consider all the directions of this finite sheet of charge where there is a chance of getting the electric flux density d bar. Now we are going to draw all those directions for this finite sheet of charge as shown in the figure. So in this direction we may get the electric flux density, that is all vertical directions of this rectangular or finite sheet of charge, and then in the top portion we may get the electric flux density, and in the bottom portion also we may get the electric flux density like this. Then by closing all these possible directions, what we are getting is a rectangular box or simply a cube. It will become the Gaussian surface, which is the closed path. Now we have to know, out of all the 6 faces of this rectangular box or cube, we have to consider the tangential components as well as the normal components. So this cube having 6 faces, the electric flux density in the right side face of the box will be like this, and coming to left side face, the electric flux density will be like this, and then to the top face it will be like this, and for the bottom face it will be like this. And here I am not drawing the front and back portion faces, because in order to avoid the complexity, if we draw these 2 directions also, the figure will become very complex and it is very complex to understand. So that's why here let us assume that the electric flux density will be having for front and back directions also, but for the simplicity of understanding we are not considering those 2. Now if you see the normal and tangential components, so towards the right face, left face, front and back faces, the electric field will be in the tangential direction for both right face and left face. For the tangential component, already we know the electric flux density is 0. But whereas for the top face, it will be in the normal direction, so it was represented as dn bar. Similarly, for bottom face also, it will be in the normal direction, so it is not 0. So in order to know the value of this dn bar, we have to apply the Gauss law. Similarly, for the portions to which we have not drawn the electric field directions, that is front and back directions also, the electric flux density will be tangential only. So to those two faces also, the electric flux density will be 0. Now, finally from the figure, what we can say is, for the rectangular box or cube Gaussian surface, the electric flux density will be tangential to the right, left, front and back faces of the cube, and it is normal to the bottom and top faces of the cube. Once we have identified the Gaussian surface, then the problem is very simple to solve. So the remaining part is only we have to apply the Gauss law to the portions where we are getting the electric flux density in the normal direction. So by applying Gauss law, which says that closed integral over S d bar dot ds bar should be equals to the total charge enclosed. Viewers, here for this closed Gaussian surface, which is a rectangular box or cube, what is the total charge enclosed, Q enclosed? Here we have considered a finite amount of sheet. Let us assume that that finite amount of sheet is having an area of A as shown in the figure. Now, to the top and bottom surfaces, the electric flux density is normal. So what will be the area for the top and bottom surfaces? Is also having the same area. The top surface will have the same area of A and bottom surface will also have the same area A. So therefore the total charge enclosed is given by, so for this entire sheet of charge having an area of A, then what will be the total charge enclosed? It is rho s into the area A. So that will become rho s into A. So that should be equals to closed integral over S d bar dot ds bar. So that we are taking here. So this normal direction is existing in z direction. So d bar we are representing as dz, and what is remaining? Closed integral over S ds bar. Now, so this can be written as dz into, so what is this closed integral over S ds bar? Don't evaluate the integral if we are using the Gauss law. This closed integral over S ds bar is nothing but the total area of top and bottom faces of the cube. So what is the area of the top and bottom? It is A plus A, that is 2A. From this you can write dz is given by rho s into A divided by A plus A, that is 2A. Now AA gets cancelled here, then in general we can write d bar is equals to rho s by 2 into, so what is the vector along z direction? Is a z bar. By considering the infinite sheet in the xy plane, you will get the d bar in the z direction, or in general, so what you can write, this d bar is d bar equals to rho s by 2. So by considering the infinite sheet in xy plane, we are getting the electric flux density in the normal direction of xy plane, that is z direction, or in general, so it may be represented as an bar, which is the normal unit vector for the infinite sheet, like this. Then here also the important point is we are not evaluating the closed integral over S ds bar integral, which is same as the total area of top and bottom faces of the cube. So that is nothing but the surface area of top and bottom faces of the cube. Our next application is infinite volume charge. As usual, let us consider a well-known Cartesian coordinate system consisting of x-axis, y-axis and z-axis. Now, this infinite volume charge problem can be solved very easily by just assuming that this infinite volume charge rho v dv was placed at the origin in the form of a point charge q. Then it is already the solved problem, that is for a point charge q. So here the assumption is the point charge q is having the total infinite volume charge rho v dv. Now by applying the Gauss law, so for this infinite volume charge which was placed as a point form as q equals to rho v dv at the origin of this Cartesian coordinate system, then the d bar will be normal in all the directions of this spherical Gaussian surface that we have already considered while we have solved the point charge problem. Now for this infinite volume charge in the form of point charge also, the same sphere will become the Gaussian surface. Now, by applying at a general point P, then we can find out the d bar for this entire spherical Gaussian surface by applying Gauss law directly. So that is closed integral over S d bar dot ds bar should be equals to the total charge enclosed q enclosed. So for this infinite volume charge, which we have assumed as rho v dv, which is also in the form of point charge, so that should be equals to d rho in the rho direction, and what is remaining, closed integral over S ds bar, and this should be written as d rho into, don't evaluate the integral since we are using Gauss law, so therefore closed integral over S ds bar is nothing but the surface area of the sphere having a radius of rho. So what is the surface area? It is 4 pi rho square. Then from this we can write d rho is given by the volume charge density rho v dy divided by the surface area, that is 4 pi rho square, or in general d bar we can write it as the infinite volume charge density rho v dv divided by 4 pi rho square, and the associated unit vector is a rho bar as shown. And here also the important point is we are not evaluating the closed integral over S ds bar, which is same as 4 pi rho square, which is nothing but the surface area of the Gaussian surface, which is a sphere. The last application of Gauss law is uniformly charged sphere. So in order to apply the Gauss law for this uniformly charged sphere, let us consider a sphere having a radius of a, which is having a uniform volume charge density as rho v coulombs for every meter cube, as shown like this. You are having a uniformly charged sphere which is having a radius of a. Then our aim is we want to calculate the electric flux density both inside this sphere as well as outside this sphere. So therefore this problem can be solved by considering two parts. One is having the rho, that is the radius of original Gaussian surface, what we are going to construct to solve this problem. So that may be either inside the sphere or outside the sphere. So first part is inside the sphere, so that means rho is having lesser than the original radius a, and the second one is having the radius greater than this original radius a. Then the first part will have the Gaussian surface like this. So that means the Gaussian surface is having the lesser radius rho than the original, and the second one is having the Gaussian surface having the radius greater than a. Then here we are having two Gaussian surfaces, one is having less than the original radius a and another one is having greater than the original radius a. Now we have to apply the Gauss law for the two Gaussian surfaces separately. Now coming to our first Gaussian surface, that is having the radius less than a. For this, if you apply the Gauss law, that is closed integral over S d bar dot ds bar should be same as the total charge enclosed. So here for this uniformly charged sphere, first we have considered the Gaussian surface covering some portion of this uniformly charged sphere. Then what is the total charge enclosed by this radius rho, which is having a lesser radius than the original radius a, is given by the q enclosed is given by integral over v rho v dv. So that we can write it as rho v into integral over v dv. So that can be written as rho v into, so since we are applying Gauss law, we won't evaluate this integral over v dv. So for this we will consider directly the volume of the Gaussian surface, which is a sphere having a radius of rho. So what is the volume of a sphere having a radius of rho? It is 4 by 3 pi rho cube. Directly we have considered the volume of the sphere without evaluating the volume integral. Then coming to left hand side, that is closed integral over S d bar dot ds bar should be considered as d rho along the rho direction into what is remaining, closed integral over S ds bar. Here also we won't evaluate this closed integral over s ds bar, so it can be considered as d rho into, in place of closed integral over s ds bar, what we will consider? The surface area of the sphere having the radius of rho, so that is given by 4 pi rho square. As usual, we have seen in many applications previously while applying Gauss law. Now these two should be equal, so that is the d rho into 4 pi r square should be equals to rho v into 4 by 3 pi rho cube. Then here 4 pi gets cancelled both sides, and you are having rho square left hand side and you are having rho cube right hand side. So this rho square will get cancelled with the rho square in the right side. So right side you are having rho v into rho by 3. So from this you can write d rho is given by rho v into rho by 3, or in general we can write d bar equals to rho v into rho by 3, and the unit vector associated is a rho bar as shown like this. Then here also the important point is we are not evaluating the volume integral as well as surface integral. In place of volume integral, integral over v dv, we have considered the volume of the sphere having radius of rho, that is 4 by 3 pi rho cube. Similarly, we have not evaluated the closed integral over s ds bar also. In place of that, we have considered the surface area of the sphere 4 pi rho square. So that is very important in this problem. Now we have to apply our Gauss law to the another Gaussian surface which is having the radius greater than the original radius a, as usual. By applying Gauss law means that closed integral over s d bar dot ds bar should be equals to the total charge enclosed. So let us calculate the total charge enclosed first. So q enclosed is given by integral over v rho v dv, so which can be written as rho v into integral over v dv. Here, even though we have considered the radius of the Gaussian surface rho greater than a, but the charge is existing only up to the radius a only. Therefore here we have to consider this integral over v dv, which is nothing but the volume of the sphere having the radius of a only, not up to rho. Even though rho is greater than a, but the charge density is not existing up to rho, it is existing only up to a. Therefore what we can write here is that equals to rho v into, in place of integral over v dv, what we can write, 4 by 3 pi a cube, not rho cube. So that's very important here. So it is 4 by 3 pi a cube. Then coming to the left hand side, that is closed integral over s d bar dot ds bar. As usual, we have calculated, it is given as d rho into closed integral over s ds bar. So which is same as the surface area of the sphere having the radius rho as usual here. So because the Gaussian surface we are considering up to rho, so therefore the surface area of this Gaussian surface will be 4 pi rho square as usual, as we have seen in many cases. Now these two should be equal. What are those two? D rho into 4 pi rho square should be equals to rho v into 4 by 3 pi a cube. So by equating this, 4 pi gets cancelled. Left hand side you are having d rho square, and right hand side you are having rho v a cube by 3. So from this you can write d rho is given by rho v into a cube by 3 rho square, or in general d bar we can write it as rho v into a cube by 3 rho square, and the associated unit vector is a rho bar as shown like this. Now here the important crucial point is, in place of integral over dv, we have considered the volume of the sphere of radius a, not rho. Please make a note here. And in place of closed integral over s ds bar, we have considered the surface area of the sphere of radius rho as usual. Right? Viewers, with this we have completed all the 5 major applications of Gauss law. They are point charge, infinite line charge, infinite feet of charge, infinite volume charge, and finally uniformly charged sphere also. Thanks for watching the video. I hope you have enjoyed and you have understood well about how to apply the Gauss law for 5 major applications. That's it for today. Thank you very much. See you in the next video. Bye bye.